Welcome to Ask and Learn.
We are given that the series AN is conditionally convergent. So in part A, we'd like to show n squared and the sum of this diverges. So a way to prove this is to go by contradiction. So here, let's just point that out there. So let's go ahead and suppose the opposite. That would be the sum of n squared AN converges. Now, by the test for divergence, this would imply that the nth term here goes to 0 in the limit. But we can rewrite this in a way that'll be convenient for us. Let's go ahead and rewrite the n squared as a fraction. And if this limit goes to 0, then I could go ahead and take absolute value here as well. So let me just go ahead and throw the absolute value there. Now we go to the limit compares test. So here's another theorem, and we have a fraction here. We know that the series 1 over n squared converges. You can use the p-test to see this. P equals 2, it's bigger than 1, and that implies that the sum converges. So in this case, limit comparison test would say, so does the series here. However, this cannot happen because in the given information, we have that this series is conditionally convergent. That means part of the definition that if you take the absolute value AN, the series will diverge. So as a recap, we suppose that it converges because we're using proof by contradiction. And under this assumption in the proof, we end up showing that the series in absolute value converges, but that contradicts the given information. So that completes the proof of part A. Okay, now let's go to the next page for part B. So just remember still the given information, I'll put that here. AN, the sum, this was conditionally convergent. So I'll just abbreviate that. And now we want to show that this is not enough. Enough information to determine if the series NAN converges. So we'll show this by giving an example, one in which it converges and then one in which it diverges. So let's look at an example here, part I. So in this case, let's go ahead and define the sum of AN the following way. Now this series is conditionally convergent. You can see that it converges by the alternating series test. But if you take absolute value, the -1 just becomes a 1. And this diverges because you can use the p-test here, p equals 1. So that guarantees sees that this example we're using in part 1 here, that it is indeed conditionally convergent. We have to check that because that is the assumption here in the problem. Now I look at the series NAN, that just becomes -1 to the n, and this diverges. And to see that, you can use the test for divergence. So here's one example in which the sum of NAN diverges. Now we'll provide an example in which it converges. This time we'll define the sum of AN. Let's go ahead and do -1 to n over, and let's do n natural log n in the denominator. So this is conditionally convergent. You can use alternating series tests that will apply convergence. But if you look at the absolute value, this diverges, and to see that, you could use the integral test. So that once again guarantees that we're under this hypothesis up here, conditionally convergent. And then now go ahead and look at the sum, NAN. That becomes -1 to the n over natural log of n, and this series does converge by the alternating series test. So we gave two examples, one in which the sum of NAN diverged, and then another example in which it converges, and that solves part B of this problem.